Hello, class, and welcome to Chapter 5, Section 2, where we talk about the electron arrangements in atoms. We'll go over that in this section for this week. I give you this whole week to take some time learning about electron configurations and electron arrangement. It can be a little confusing at first, so I'm hoping, with reading the textbook, watching this lecture video, you feel a little bit better about it, especially to answer your discussion question and for the quiz questions. So the ways in which electrons are arranged in various orbitals around the nuclei of atoms are called electron configuration. And we have three rules: the Aufbau principle, the Pauli exclusion principle, and then the Hund's rule. And they'll all tell you how to find the electron configuration of those atoms. So the Aufbau principle says that electrons occupy the orbitals of the lowest energy first. In the Aufbau diagram, each box represents an atomic orbital, with the lowest energy level being way at the bottom and increased levels of energy moving top. So this is saying that electrons will always occupy the 1s orbital first, and then will work their way up, filling the next energy level orbitals as the atom number of energy levels of the various atomic orbitals, and orbitals of greater energy are higher up on the diagram. The range of energy levels, the energy levels of another principal level. So as you can see here, the range of energy levels within the principal energy level can slightly overlap the energy levels of the another principal level. So for example, the 2s, the 2p is slightly higher, 3s, 3p, 3d is overlapping with the fourth primary energy level. The Pauli exclusion principle says that an atomic orbital may describe at most 2 electrons. And to occupy the same orbital, the 2 electrons have to have opposite spins. So in your textbook, you've been seeing these electron orbitals with arrows pointing in opposite directions. That is part of this Pauli exclusion principle, that 2 electrons in the same orbital must have opposite spins. And we denote that with opposite kind of arrows going in opposite directions. So to occupy the same orbital, 2 electrons must have opposite spins. That is, the electron spin must be paired. Spin is a quantum mechanical property of electrons and may be thought of as clockwise or counterclockwise, and a vertical arrow indicated an electron and its direction of spin. So up and down means the spins are opposite. An orbital containing a pair of electrons then is written as up arrow and down arrow, signifying that those electrons have opposite occupy orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. So Hund's rule says that 3 electrons would occupy 3 orbitals of equal energy as follows. And then electrons would then occupy each orbital so that their spins are paired with the first electron in the orbital. So we first fill up the orbitals of equal energy, direction spins, and that's how we fill up the orbitals. A convenient shorthand method for showing the electron configuration of an atom involves writing the energy level and the symbol for every sublevel occupied by an electron. You indicate the number of electrons occupying that sublevel with a superscript. So for hydrogen, for example, it has only 1 electron. So in setting up the diagram, we would only put 1 up arrow in that 1s orbital because there's only 1 electron in hydrogen. So we would say the electron configuration for hydrogen is 1s1, signifying it's 1 electron filling up the 1s orbital. The sum of the superscripts in the electron configuration will always be the number of electrons in that atom. So we always want the number of these superscripts to be equal to the number of electrons in that atom. So So we start by filling out the orbitals. Up and down for the 1s, that's 2 electrons. Up and down for the 2s, that's 4. And then we fill it up this way. Remember, in the same kind of subheading of the principal orbital level, we fill up the 3 orbitals first before we go on. So this is 1, 2, 3, 4, 5, 6, 7. Where does the 8th electron go? Now we go back and fill up the opposite spin paired electron. So the electron configuration would be 1s2, 2s2, and then 2p4 because we have 4 electrons filling up that orbital. And this is how we would write out the electron configuration, remembering that the sum of superscripts, 4 plus 2 plus 2, should always equal the number of electrons. So let's go through a sample problem. Pretty easy. Writing electron configurations. The atomic number of know that there are 15 electrons. There is a maximum of 2 electrons per orbital, and electrons do not pair up within an energy level until each orbital already has 1 electron. So let's apply the concepts. Let's use our Aufbau diagram to place electrons in the orbital with the lowest energy 1s first. So there we get rid of 2, 1, 2. Apply the concepts. We'll continue putting electrons in each orbital with the next higher energy level. So we'll add 2 more to the 2s level, and then we'll continue filling up. But remember, we fill up each individual orbital first, and then we add in the downward paired electron. So what are we at so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We still need 5 electrons, so let's go up and down with 3s. 11, 12, but then 13, 14, 15 is how we'll add in the other final 3 for the 3p orbital. So the electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p3, remembering that all superscripts should equal 15 for phosphorus. So 5, 11, 12, 13, 14, 15. Exceptional electron configurations. You can obtain the correct electron configurations for the elements up to vanadium, the atomic number 23, by following that Aufbau principle for orbital filling. If you were to continue in that fashion, however, you would assign chromium and copper the following incorrect configurations. So there is kind of a point at which we need to change our process for doing this. The correct electron configurations for chromium and copper would actually be this. And these arrangements will actually give chromium a half-filled D sublevel and copper a filled D sublevel. So just keep that in mind. There are a couple of exceptions to that electron configuration rule. Some actual electron configurations will differ from those assigned using the Aufbau principle, because although their half-filled sublevels are not as stable as a filled sublevel, they are more actually stable than other configurations. So we have some exceptions to this rule because the half-filled sublevel are not as stable as the filled sublevel, but it's still more stable than any other configuration. All right, good luck with this lesson this week. Let me know if you guys have any questions, and God bless your study.